All right, we did about half these notes in class, and I could tell that no one was really paying attention. So the rest of them will be on video here. If you are watching this, make sure you spread the word that you'll get a question on Monday that'll be based on having watched this video. So we finished the front page. At the very bottom of the front page, you see these three equations. This is for the mean, variance, and standard deviation of a probability distribution. We're going to be using them on the next page, but you'll see them on the bottom of the front of your notes page there. So at the top of the back page, we have example 4. It's showing us a probability distribution, and this is based on Mendel's P experiment, which is seeing how many green offspring peas we have when we're generating 5 peas. So you may have learned about this in biology. It's a very famous experiment. You use it with like Punnett squares and that type of thing. But in this particular problem, we're generating 5 peas. The particular probability for a single pea to be green is 75%. So the probability that we have all 5 peas being green is about 23%. The probability that 4 of the 5 will be green is around 40%, 3 being green, 26%, etc., all the way down to 0 being green, very unlikely, 0.001%. So the question is, what's the mean number of peas that we'll get from these 5 peas being generated? What's the standard deviation for the number of green peas? And then along with that, what's the variance, which we need to calculate on the way to finding the standard deviation? So if you look back at the equations on the front, the mean is based on x times p of x. Now x is the number of green peas, so it's one of those numbers 0 to 5. P of x is the probability associated with getting that number. Okay, so we want to make a column where we're going to find x times p of x. So for example, 0 times 0.001 is 0. 4 times 0.396, 1.584. Okay, all these numbers is this column times that column. For variance and standard deviation, we're doing x squared times p of x. So we take the number in this column, we square it, and we multiply it by the probability. Once we have those, we can find the mean, variance, and standard deviation. So the mean is the sum of x times p of x. So we have this column filled out. We're going to add those all up. The sum of x times p of x is 3.52. That's the mean number of green peas we would expect to get from 5 offspring peas. Variance, this is along the way towards calculating standard deviation. Standard deviation is just the square root of the variance. We always have to find variance first. So for this, we find the sum of x squared times p of x. So it's the sum of this column. But after we find that, we're going to subtract the mean squared. So we need to use what we found for the mean. The sum of this column is 15.004. That's what we have here. And then the mean squared was I wrote that wrong, 3.52 squared. So 15.004 minus 3.52 squared, 0.9265. Standard deviation is just the square root of that number, 0.9625. Actually, hold up. It's not this number that's wrong. It's this one. This one should actually be 3.752. That's the sum of x times p of x. When it comes to classifying data values as usual or unusual, this is a subject that we've talked about before. So the first way to do it is using the standard deviation. Anything beyond 2 standard deviations from the mean is considered unusual. So in example 4, we found the mean and the standard deviation for the number of green peas. We could then use that information to determine if a certain number of green peas is unusual, being that it was farther than 2 standard deviations from the mean. Another way we can do it is with probabilities. If an event has less than a 5% chance of occurring, we consider that event unusual. In example 5, we're talking about flipping a coin 10 times, looking at the standard deviation and the mean. So the mean number of heads we would get when we flip a fair coin 10 times would be 5, with a standard deviation of 1.581. Based on those results, would it be unusual to get 8 heads in those 10 coin flips? If we move out 2 standard deviations from the mean in both directions, so we take that mean, which is 5, that's half of 10, makes sense, we have a 50% chance of getting heads. So subtract 2 times the standard deviation, we get 1.84. Add 2 times the standard deviation, this would be our maximum usual value, 8.16. 8 is within this range. It's not more than 2 standard deviations away from the mean of 5. So no 8 heads in 10 flips is not unusual. Back to that question regarding the green pea pods. Is it unusual to get just one green pea? So let's say we don't have the standard deviation and the mean, we're just looking at this probability distribution. First off, when we're talking about an event being unusually low, so if it's unusually low to get one green pea, it's also unusually low to get 0 green pea pods. Okay, so we want to combine these two probabilities together because it would be unusually low to get either of these if it's unusually low to get one. So that being said, those two probabilities combined gives us 0.016. That's less than 5%. It would be an unlikely event to occur. So getting one green pea pod is unusually low because it's less than 5%. When we're talking about the expected value, we're referring to the mean. It's the same thing, and we find it the same way with that exact same equation. Expected value is the mean. This question should look familiar. Let me show you how we set up the probability distribution, and you can see if you got those questions right in class today. So to start, I'm going to incorporate the money into this distribution because it's asking to find the expected value of his profit along with a standard deviation. So to start off, we have 3 results here. So this horse can lose both races. He could win both races, or it could win one and lose one. So winning both, it gives us probabilities for each scenario. So it says there's a 20% chance it wins the first race, a 30% chance it wins the second race. We're going to multiply those two and get 0.06. Okay, we take the complement of those. If there's a 20% chance that it wins the first race, it means there's an 80% chance that it loses. Same thing with a second. There's a 30% chance it wins, meaning a 70% chance it loses. So losing both races would just be those two numbers multiplied, 0.56. Now this distribution has to add up to 100%. So 0.56 plus 0.06 is 62%. This has to equal the remainder, 38%. The other way we can get this, if the horse wins one race and loses the other, it can do it in either order. So it's going to win the first race, 20% chance, which means it loses the second. There's a 70% chance it loses the second. Okay, or it could do the opposite. It could lose the first race and win the second. Or is addition, add those two together, and we'll get that same 38%. Now up top, these numbers are coming from the profit that we expect from each of these scenarios. So for example, it says the man purchases this racehorse for $20,000. If the horse wins both these races, the horse is expected to be worth $100,000. In that case, the profit will be $80,000. If the horse wins one of the races, the horse will be worth $50,000, meaning a $30,000 profit. And if it loses both, it'll be worth only $10,000. So the man lost $10,000. So to find the expected value of his profit, we're just finding the mean for his profit, which is x times p of x. So we take each of these profit values, multiply it times the probability, and then we're going to sum up this column. That results in an average profit, a mean profit, or expected value of $10,600. Now, he can't actually make that amount. He's either going to lose $10,000, win $30,000, or win $80,000. But over the long run, if he were to do this many, many times, it would average out to winning $10,600 on average. It also asks us to find the standard deviation for his profit. Now, just as a reminder, standard deviation is the average amount that our values vary around the mean. And the standard deviation for these is pretty large because he can have a pretty big profit or like a moderate loss. So when we look at this, again, we always have to find the variance first because if we just add these up, some are negative, some are positive, they would cancel each other out. So the way we counteract that is we square all our differences and then we add them together. Squaring them makes them positive. That's what the variance is. But Variance we don't really like because now we're dealing with squared units. We're working with dollars squared, which doesn't really make sense. Okay, but for variance, again, it's x squared times p of x. So it's the negative $10,000 squared times 0.56. So we start to see some really huge numbers here. 30,000 squared times 0.38, 80,000 squared times 0.06 gives us huge numbers in the hundreds of millions. Once we add all these up, we're subtracting the mean squared, 10,600 squared, and that gives us a variance of 669,640,000. That's in square dollars. Standard deviation is the square root of that number. Our standard deviation is $25,877.40. This is telling us how spread out our data is, and to be more specific, it's telling us the average distance from the mean for all of our data values. It makes sense that this is a big number, especially when viewed in relation to our mean. It's more than twice as big as our actual mean is. When we look at the range of values, we can win 80,000 to lose negative 10,000. That's a big range, so it makes sense that we'd have a large standard deviation.